Hello, hi, I'm Vanilla. Today we are presenting the topic Morpheus towards automated SLOs for enterprise clusters. So this is given from the members of Microsoft and the University of Illinois at Urban Campaign and University of Freiburg. So they proposed this model because they face the challenges in managing multi-tenanted clusters for running businesses' critical data analytics jobs. So these challenges arise due to unpredictable nature of job runtimes, causing missed deadlines and negative business impacts. So the unpredictability of these job runtimes can be attributed to two main sources, such as sharing induced variability, which is like this is caused by inconsistent allocations of resource across job runs, often resulting from scheduling policy artifacts. And the second attribute of this is inherent variability. This type of variability is intrinsic and can be due to be various factors such as changes in job input and modification in the source code, failures, and hardware changes. And Morpheus mainly motivated from the modern resource management frameworks for a large-scale analytics leaves unresolved problematic tension between the high cluster utilization and job performance predictability. So Morpheus addressed the tension between these two by codifies implicit user expectations as explicit service level objectives like SLOs and enforces SLOs using novel scheduling techniques that isolate jobs from sharing induced performance variability and mitigates inherent performance variance by means of dynamic reprovisioning of jobs. So this is the main motivation of the amorphous paper they have created, and these morphous tackles like few challenges, like three primary challenges, like inferring SLOs and modeling job resource demands, like capturing user predictability expectations. Like the implicit user predictability expectation is an explicit form of that is actionable for the underlying resource management infrastructure. And the second challenge they faced is controlling sharing induced unpredictability. Like this consists of controlling performance variance with a minimal resource over provisioning. And the third challenge they faced is like coping with inherent unpredictability. Uh, we do this by dynamical reprovisioning the current instances of the reservation in response to the job resource consumption in relation to the SLO. And importantly, Morpheus techniques are framework independent, making them applicable across the multiple application frameworks within production clusters. This independent allows the system to be used effectively in diverse computing environments, supporting various applications without being tied to a specific software framework or technology. And coming to the project of like Morpheus, the initial stages of the project where the team aimed to validate their informal assumptions regarding the operations and usage of big data clusters. They conducted this assessment by analyzing four primary data sources. So those are the first one is execution logs, uh, which are analyzing execution logs of millions of jobs running on a clusters with over 50,000 nodes. These logs likely contain detailed information about the task, job run times, resource usage, errors, and the other relevant metrics. And the second thing they have focused with a data source is infrastructure deployment and upgrade logs. Examining logs related to the deployment and upgrade of the infrastructure supporting these big data clusters. This could be include information about changes, improvements, or maintenance activities performed on the cluster's hardware or software. And the third data source is interviews, discussions, and escalation tickets. Gathering information from interviews, discussion threads, and tickets involving users, operators, and decision makers. Inside of these interactions could provide a qualitative data about issue phase, user experiences, operational challenges, and decision-making process related to the cluster usage and management. And the last data source they have used is targeted micro benches. We're connecting specific micro benchmarks to evaluate, measure certain performance aspects of the clusters. These benchmarks might have been designed to assess particular functionalities, capabilities, or limitations of the clusters in the control environment. By utilizing these diverse data sources ranging from large-scale execution logs and the infrastructure records to qualitative feedback from stakeholders, and the team aimed to gather the comprehensive understanding of how big data clusters were operated and the challenges faced by the users and the operators and the actual performance and the behavior of these clusters in the real-world scenarios. This approach likely helped in validating or disproving their initial assumptions and forming a more accurate understanding of the operational landscape of these clusters. And coming to the data analytics, like the main work they have did is like after the process of these data analysis conducted on the cluster workloads, they reveal like a few crucial insights. Those are like cluster workloads where the workload composition is like the majority of the workload and provisioned capacity is dedicated to the production jobs, and ad hoc jobs and resource allocated for handling growth or failures constitute the remaining capacity. Any unsigned capacity is fairly redistributed to expedite job completion. Next, next one is escalation priorities, where escalations, which is mostly related to the production jobs, over 90% significantly affect users' concerns, especially those related to the performance predictability. Users are 120 times more likely to complain about their unpredictability of job performance compared to the issues of fairness in the resource allocation. And nature of production jobs. A sustainable portion, like over 60% of jobs, is larger clusters exhibit recurrent behavior, often operating on continuously incoming data. The jobs tend to be a periodic in nature with distinct peaks in the distribution of job periods, like once in a day or once in an hour. The scheduled job submission. So the job start times exhibits a dense distribution around specific timeframes, notably the start of the hour. This pattern comes from the majority of the jobs are automatically submitted on the fixed schedules. So the overall, these findings highlights the significance of the recurrent production jobs within a workload. Understanding this current nature is essentially for effective cluster planning, allowing for more efficient resource provisioning and allocation without overly conservative measures. Leveraging the periodical and recurrence of the jobs, and the cluster can be better managed, optimizing resource utilization and scheduling to accommodate the workload's characteristics efficiently. The same like the predictability challenges are faced. The challenges encountered in manual tuning job allocation within big data clusters, like shedding light on the difficulties users facing in optimizing the resource provisioning for their jobs, or like distribution of the resource provisioning. So based on the picture, we can feel like the display ratio between the total resources provisioned by a job owner and the actual resource usage, showing a wide range of over and under allocation. This indicates the challenges users encounter in optimal provisioning resources of their jobs. Around like 75% of jobs are over provisioned, and within 20% of them are being exclusively over provisioned, like over 10 times the required resource. Additionally, a significant portion of periodic job doesn't change their resource provisioning settings over time, contributing to over provisioning. And where it comes to the source of performance variance, understanding the source of performance of variance is complex. Like an analysis of production logs shows a small positive correlation between increased resource sharing and runtime variance, suggesting that increased sharing impacts runtime variance. A micro benchmark experiment in the figure on TPCH queries in difficult configuration demonstrates that even when common source of inherent variability are removed, runtimes remain unpredictable due to the factors like stragglers or other reasons not related to the data availability or network congestion. So based on these findings and experiments, the conclusion drawn are like modeling normal behavior, where history-based approaches can effectively model the typical behavior of a query. And the next one, they have concluded like a dynamic handling of outliers, where handling outliers and unpredictability without resource waste requires a dynamic component for online reprovisioning when a job behavior deviates from a normal pattern. And the third conclusion they have derived is need to a generalized solution. While addressing individual source of variance might be possible with specific solution, having a general purpose defense mechanism against unpredictability and outliers become crucial for effective mechanism management and optimization of job runtimes in the cluster environment. And the paper suggests that while historical data and specific solutions can address certain aspects of variance, a comprehensive and adaptable solution is essential to address the diverse and unpredictable nature of the runtimes in big data clusters. So this could involve a dynamic system capable of adjusting the resource provisioning in real time based on historical patterns and deviations to ensure efficient resource utilization while meeting the performance expectations. And coming to the changing conditions, the evolving nature of the conditions within the cluster environment, emphasizing the challenges arising from changing hardware configuration and evolving user scripts. So the hardware churn and impact job runtimes, like the cluster conditions keep evolving. Jobs may run on different server types. Uh, from the figure C, we can illustrate that the hardware churn in the cluster showing the changing ratio between the different machine configurations, like stock keeping units (SKUs) over a year. Even seemingly minor differences between hardware configurations can have a significant impact on job runtimes. For instance, a Spark production job might experience a 40% difference in runtime when executed on a different SKUs, like a stock keeping units. And the next one is evolving user scripts, where analysis of the user scripts or user-defined functions (UDFs) reveals frequent changes in code versions. A significant portion, like 15 to 20% of the periodic job experience substantial code alterations, like more than 10% code difference within a month. Additionally, over half of these jobs encountered small code changes, breaking the MD5 of the parameter stepped code. And these frequent changes indicate that any spatial optimized resource tuning is likely to become suboptimal over time as user scripts continues to evolve. Given the evidence of the evolving cluster conditions and the impact of job execution, the focus shift towards constructing a resource management infrastructure that prioritizes predictable execution as a fundamental requirement. And this emphasizes suggests a need for a resource management system capable of adapting dynamically to changing hardware configurations and involving user scripts while ensuring consistent and predictable job runtimes across these changing conditions. And we can clarify whether these motivations is worth or not. So the different users might have a varied expectations, and the system should consider them. Like they need to consider all of the user expectations, and predictability over fairness may not always work. Just because something works in the theory or control may not work for the next one too, and does not detail how extensively users have been involved in the solution. And coming to the main part of the Morpheus, where like what the part they did in the Morpheus, observing and learning from the execution of periodic jobs over time within big data clusters. So it outlines the key functionalities involved in the governing the life cycle of periodic job, which is referred as a JobX within the Morpheus framework. So the first one is a job. The life cycle goes like this: like job submission and infrastructure capture. So users periodically submit JobX with manual provision resource. The underlying infrastructure captures like the data dependencies, ingress operations, and the provenance graph, like PG. It's known as PG. The resource utilization of each job run stored as R1 and R4 skylines within the telemetry history database. And the second one in the life cycle is SLO inference. An offline analysis is performed on a successful job extents, which is a periodic job. The PG graph helps derive a deadline SLO for a job X, which we can denote that as a D, as it is a deadline. From the from the TH telemetry history, Morpheus derives a model of the job's resource demand over the time, which is termed as R. The next life cycle plan is a user confirmation and model adjustment. So the system presents automatically generated SLO and job resource model to the user for confirmation or optional user overrides. And the next one is enforcement of SLO via recurring reservations. So Morpheus enforces SLOs by creating recurring reservations for JobX within the cluster agenda based on the job resource model R. And a new instance of these JobX, like a periodic run, runs with the recurring reservations, ensuring dedicated resource for the job. The next one in the life cycle is the dynamic reprovisioning, where the dynamic reprovisioning component continuously monitors the progress of the JobX online. So it dynamically adjusts the reservation size to mitigate inherent execution variability during a job runtime. And the last step in the life cycle is a continuous learning and refinement. Morpheus continuously updates its knowledge base, like it feedbacks PG and telemetry information from a new JobX runs into step 2 for a continuous learning and refinement of the SLO and the job resource model. This life cycle reflects Morpheus and adaptive nature. where it learns from the past job executions, derives SLOs, models resource demands, enforces reservation, and dynamically adjusts to changing conditions to ensure predictable execution for periodic jobs within the cluster environment. The system operates in a continuous loop of learning, planning, execution, and refinement to optimize resource utilization and meet performance expectations. And coming to the components of the Morpheus system uh, comprises several components operating at a different time scales to manage the job execution within the clusters efficiently. Here's an overview like of components and their functions. The first component, which comes like an the first one we can, we have an automatic inference module, but it's molded with the two more things in it. Those are extractor of target SLOs and job resource model. So coming to the extractor of target SLOs operates on a PG, it's a provenance graph, capturing data dependencies and ingress operations, derives deadline for a periodic jobs based on a precise timing information stored in the PG. These deadlines indicate the time at which downstream consumers read a job's output. And the second one is a job resource model, utilizes a detailed telemetry information on job runs, including the time series of resource utilization, which is a skyline, and constructs a tie envelope around the typical behavior of a job based on the time series for a multiple runs, determining the typical resource demands and the job behavior. And coming to the next part of these components, it is a reservation placement. So reservation placement expresses SLOs and job resource models as a recurring reservation request handled by a reservation placement mechanism. It extends to YARN's reservation system, specifically accommodating periodic reservation, employs an online packing algorithm specialized for a periodic jobs, efficiently allocating resource for incoming jobs without modifying the existing allocation. And the last part of this is dynamic reprovisioning, where it monitors job progress concerning the reservation consumed, automatically adjusts the reservation by tweaking the provision resource if job progress deviates significantly from the expected rates. So this adjustment handles inherent unpredictability in job execution dynamically, irrespective of the framework used. So the dynamic reprovisioning component ensures that the reservation initially set to based on the input models adapt dynamically to job execution characteristics. So this black box approach is a framework independent, allowing it to handle variations in the job progress or a behavior across the different frameworks, and commonly used within the cluster without relying on a specific framework details. So this adaptability ensures better resource utilization and helps mitigate issues arising from unpredictable job execution behavior. And coming to the limitations of these Morpheus, uh, the first limitations can be termed as like a control over globally shared resource. Morpheus operates within the boundaries of underlying resource management infrastructures such as like Apache Hadoop or Yarn. So it lacks direct control over global shared resource like bandwidth on switches or DNS servers. And the runtime variability caused by the globally shared resource is managed through the dynamic provisioning, reprovisioning, as Morpheus can't directly control them. And the second limitation is support for a non-periodic jobs. Morpheus is designed to support both periodic and non-periodic reservations. However, it doesn't automate the extraction of SLOs and job resource models for jobs that have not been previously observed. And the third one is automatic SLAs, where Morpheus provides foundation elements but doesn't aim to deliver fully automated service level agreements. A complete SLA involves specifying economic or business aspects to provide user agreement, including resource cost, SLO attainment, thresholds, legal and financial consequences of missing SLOs, and limits on dynamic reprovisioning and charging implications. So to address these limitations and advance Morpheus, we can do like research and integrations, where Morpheus could explore integrating approaches for recent literature that enable prior job schedule modeling, prior job resource modeling for unseen job types. This integration could enhance its ability to manage non-periodic jobs efficiently. And the second one they could do is expanded scope. Like further research and development could focus on extending Morpheus to encompass broader SLA-related aspects, considering economic and legal factors, thresholds of SLO attainment, cost implications to ensure usage, and constraints on dynamic reprovisioning. By evolving to integrate advancement methods for a priori job modeling and expanding its scope to encompass a more comprehensive SLA framework, Morpheus could overcome these limitations and enhance its capability for managing diverse job types and accommodating various business and economic consideration within its resource allocation framework. And the further idea of the Morpheus could be continued by Mahidar.
Designing of SL2 interface, the user experience expectations. Use consider job completion by a deadline as a critical metric, and periodic jobs isolated based on the uh, criteria like job names, source code, and signatures, and inter-arrival times. And Morpher's objectives. Morpher aims to define the acceptable to job performance throughout the automatically generated target service location objects. They are SLOs. Provision graphs. Provision graphs, the primary interface tool employed is an provision graphs. This periodically job isolated based on the criteria. Sorry, Vendors target services like objectives as well as the primary interface tool employed is in provision graph. Notes in this PG represents the jobs and files where edges capture read, write operations and violations. Isolate periodic job. Next slide. No, change the next slide. Isolate periodic jobs. Isolate periodic jobs are grouped on based on the exact job names, appropriate source code, signatures, and nearly constant inter-arrival times. The evaluation of the grouping involves the coefficient of variation CV measures for inter-arrival times. Estimated SLOs for PGs. Uh, the object to determine the earliest start time as AJ and deadline was DJ for a job. T random variable. T in available of job inputs. T start job start time. T and job completion time. T out read time of the first job output read. SLO derivation. SLO derivation was the threshold of CV. T out read and median of T out read minus T and by T n minus T cut. Uh, Derivation AJ and DJ as percentiles of T in aval and T out read distribution. The majority of periodic jobs with deadlines receive inferior SLOs with other continues with manual resource provisioning. Next slide. Job resource model, allocation. Morpher seeks to determine an optimal resource allocation for periodic jobs. The optimization process is influenced by the parameters of alpha belongs to 0, comma 1. Regulation, the reduction of over allocation. Optimization objective. Skylines denoted as SI, comma K represents the average contents used at each time steps K for individual job instance. The objective function aims to minimize the efficiency balance for over allocation and under allocation. The over allocation penalty was denoted by A naught and under allocation penalty was denoted by AU. The over allocation penalty, the metric of the average over allocation constraints across the instances and time steps. It penalizes the resources allocated in a time step that remaining unsent and cannot be reclaimed later. Under allocation penalty. The under allocation penalty captures the instance where job comprehension for storages, shortages and accumulation debit over time. The penalty is computed as the average debit at the last time step. Avoiding lazy solutions. A A regularization constraint is implemented to prevent a strategy of lazy under provision compressed by aggressive allocation towards the job competition completion. The constraint ensures that the average normalized underallocation remains below a specified threshold. Transformation of LP. Despite the presence of nonlinear terms, the optimization problem is translated into a linear programming task through the standard transformation. Tracking multiple periodic jobs. They are divided into three: periodic reservation, problem formulation, tracking multiple periodic jobs. We can go with the periodic reservations. In periodic reservation, partially challenges the issues. Allocation resource for multiple instances of periodic jobs. Inefficiently calculating the sorting separate reservation for each instance. Enhancing predictability. Despite reducing flexibility by fixed offset improves predictability for the users. Result is an repeating pattern in overall allocation of the periodic jobs. Identifying the unit. Identifying and storing the small repetition unit capability patterns for all periodic jobs. Utilize the least common multiple LCM of time periods of the length of internal storage unit. Algorithm efficiency. Focused approach was efficiently gained by concentrating of the LCM representation. Addressing con about a large LCM due to the sliding of filter periods. Partial lie approach set LCM to 1 day elegance with the distribution of periods in the cluster. Handling lines, outer lies, instance which periods are not aimable to 1 day LCM get non-periodic reservations. Adaptability of LCM, flexibility of highlight, emphasizing the LC. Problem formulation. For formulation, we need to set an input and the input period job and time range 0 to T, representing the LCM period. Job relevant, job reviled in one fashion, one by one. Job characteristics. Each job characteristic started start time was AJ and deadline was DJ and stages were K belongs to 1 comma KJ. The objectives are goals to allocate the containers to meet job requirements by the deadline, minimize waiting time for non-periodic jobs, balance load for accommodation future jobs. Objectives of low cost, minimize maximal total allocation over time. Constraints, no rescheduling of jobs already in the system for a business continuity. Entire allocation must be continuous, no holes allowed. Requirement and approaches. NP had offline schedule problem. Online schedule is challenging even for single stage jobs. Requirements for the packets of algorithm. Packing algorithm. Main requirements. Quick and lightweight solution due to the frequent updates in the reservation play by Morpheus. Increment solution. Study reservation for ext- exciting the job without sustaining resources determine the challenges. Offline version can be formulated as a mixed integer line programming. Next slide. No, no, next slide. Packing with low cost. Cost function. Low cost utilizes a cost-based approach for container allocation. Cost function. Consider the current cluster allocated the resource demanding of each job at the time slot of T. Basic algorithm. Low cost aims to allocate the incomplete jobs efficiently in the terms of cost with represent sorry cost of with recent max T C of T. Greedy procedure. Containers are placed iteratively at the coefficient position. Allocation handling for the time interval. Periodic jobs may have multiple instances within the LCM. Analysis consideration. For analysis purpose, assuming all periodic jobs have the same skyline requirement enables an isolated examination of the consequences of the choice. Remaining path will continue by Nana.
As mentioned before, dynamic reprovisioning in Morpheus focuses on addressing the unpredictability in task execution that cannot be mitigated by reservations alone. Reservations in computing systems are used to allocate resources to specific tasks, reducing unpredictability caused by resource sharing. However, they are less effective against unpredictability arising from external factors such as infrastructure problems or changes in job requirement. Dynamic reprovision is introduced as a solution to adapt to these kinds of unpredictabilities. It involves real-time adjustment of resource allocation to ensure that service level objectives are not violated. Dynamic reprovision algorithm. Um, it focuses on continuously monitoring the resource usage on ongoing jobs. It adjusts the skyline of allocated resource dynamically. The skyline represents the current allocation profile for resources across various tasks. The algorithm triggers a response when it detects a job is running slower than expected, indicating a potential risk of not meeting SLO. In response, DRA temporarily increases the resource allocation for that job. The extra resources are allocated based on the job's immediate demand but are capped to prevent excessive allocation. Additional resources are typically provided for a short defined duration after which the allocation is reassessed. DRA updates the current instance of jobs reservation with this additional allocation, ensuring that the job does not exceed its resource request. This was one of the examples that was demonstrated using TPCH query 1, a standard database query used for benchmarking. The query execution resource consumption is represented in this graph to illustrate how DRA manages resources. As you can see with the blue, red, and green running on 2200 parallel containers. The DRA addresses struggling tasks and delays in the job stages, allowing them to complete efficiently. It also enhances the success of dynamic reprovisioning adjustment made to low-cost function. This function is part of resource allocation. The adjustment involves optimizing resources allocation concerning the job starts and deadline times. This is particularly important for handling variability in data availability. Implementation. Um, implementation. This module was integrated into Hadoop, Yarn, and challenges. Um, so the functions it came with three components, main components for the implementation of of Morpheus. The first one is automatic inference engine, which operates as a standalone service, utilizing provenance and telemetry data to automate the submission of reservation requests. Um, it connects to the resource manager of Yarn using a REST endpoint, enabling dynamic and automated resource handling. The second one is reservation placement component. It's part of the resource manager in Yarn, which implements a low-cost algorithm responsible for the strategic placement of reservation, which ensures efficient and effective allocation of resources within the Hadoop and Yarn environment. The last one is the dynamic reprovisioning mechanism, which is implemented as a monitoring thread within the RM, which continues observes job resource requests and dynamically adjusts reservations based on real-time resource needs. This is designed to highly be pluggable, allowing for customization to suit specific framework requirements or characteristics. Um, some of the challenges that came was the scalability of Morpheus, primarily because Yarn scheduler was initially designed for a smaller and less dynamic set of queues. The solution that was implemented was the locking mechanism of RM scheduler, which introduced finer granularity locking and adoption of lock-free data structures, in which the RM's asynchronous, event-driven nature significantly enhanced and scalability. Um, this improved, this improvement enabled Morpheus to effectively operate within a large-scale environment such as a 27-node cluster. It also handled cold start scenarios where it addressed how to manage new and non-recurrent jobs within Morpheus, ensuring that new and one-off jobs can still run effectively using existing fair queuing infrastructure within Yarn. Um, some of the expectations, these are some of the evaluations that were gathered after the experiment. One of the key aspects of evaluation was first performance of enterprise trace, which demonstrate the ability to extract SLOs, derive job resource modules, achieve high SLO attainment, and efficiently pack reservations. It also ensures high utilization and reduces cluster costs by handling the complex skyline produced by job modeling component. The second one is breakdown of contribution, which is using the SLOs extraction job modeling to lower cluster size by 16%. At the same time, it used the dynamic reprovisioning to deliver 13 times lower violation or reduce cluster size by 6%. The third one is physical deployment and skill test using the Hadoop trace and TPC H workloads. It was able to test three cluster environment, one from the 275 node cluster, the other one 2700 node cluster, and the other 4000 cluster, which controlled the runtime variability while outperforming jobs with reservation protection. Some of the findings and impacts that that was discovered. Morpheus was able to successfully address issues related to job scheduling and resource allocation in large-scale cluster environment. Um, it successfully addresses critical challenges in job scheduling and resource allocation um, in areas where systems struggle. Its scalability and effectiveness across various workloads from standard benchmarks to real-world production scenarios stand out. The versatility is crucial for practical deployment in diverse computer environments. In conclusion, the implementation of Morpheus suffocated integration into Hadoop addresses key challenges such as scalability and the management of cold start scenarios.